Welcome to the pre-recording of lecture 39 in the 8-week summer session, Introduction to Computer Science. So lecture 39 is the first half of the 20th session in this 8-week. So we are at the end of the 7th week. So this lecture is scheduled for 28th of July. So in the last session, we talked about concurrency and parallelism. So Python provides concurrency with multi-threading, which is very nice if one needs to model independent actors, but one doesn't get real parallelism. In the second half of the session, so lecture 40, I will illustrate how to use the multiprocessing module. This lecture serves as an introduction to network programming. We already introduced client-server computing or server-client computing. In Python, we can experience this. So at the end of this lecture, I will demonstrate a very simple game of two Python programs communicating with each other. So this is defined via the socket module in Python. Sockets also are used in the network programming world. Python provides a very nice abstraction, a very nice layer on top of this. Okay, so there will be two parts in this lecture. So the first part is mainly concerning the terminology. So let's talk about transmission media. So the units for speed is bits per second. So this is historically in the very earlier times. Telephone wires for telephone communications were used, and then one was measuring 1,000 bits per second. That was good for telephones. Now for television signals, you actually need a lot more. So this gave 10 million bits per second, but what can still reach one magnitude, a significant magnitude higher, 1 billion bits per second when one uses optical fibers. So we also have wireless communications. There, the bits per second is actually not really measured. So the communication that I typically use is a wireless network, which is already fine, but it's kind of in between the optical fibers and the copper wires. So these are the four different categories that we distinguish for characterizing transmission. They are characterized in terms of speed. Optical fiber is the fastest speed. Copper wires for telephone, the slowest, and in between somewhere the wireless. Oops, somehow pressed the wrong button. So let's go to the topologies. So in a client-server topology, you could put your, so you can put your server right at the center. So this is the star network. When there's really one computer, probably the most powerful one, who's going to serve all the other nodes in the network. A ring topology is also so the problem with the star network, if the center of the network drops out, then everything is lost. So there is no connection. With a ring network, you can actually still, if one connection is cut, then one can still go the other way around. And then there is also the bus network. The bus, and we mentioned the word bus when we talked about the von Neumann architecture. This is where all the nodes are lined up. So these are three most common regular topologies. When it comes to supercomputers, people often still think of hypercube topologies. So you have a square, you have a cube. Imagine a computer sitting at the corners of a square, sitting at the corners of a three-dimensional cube. And this is a structure that can be generalized to any dimension. These hypercompute topologies have the benefit that the number of nodes that need to be in between two nodes depends logarithmic on the total number of nodes. So just to say that the slide actually only gives a very basic introduction to many concepts in network topologies. Client-server architecture is a way, or client-server computing is a way of computing where one computer acts as the server and the other computer acts as the client. In computing, it could also be that the server is acting somewhere as the manager to distribute work to the client computers connecting to the server, and where the server is orchestrating something, is coordinating that all the clients do relevant proportions. But however, client-server architecture is mostly for providing a service. It could be a software server, so some people are using Jupyter Lab in the cloud, so this is cloud server, web servers, and also database servers. So these are software services. You could also offer hardware services. In many buildings, printers are shared. So you could have a print server where computers connect to the printing device, sending what needs to be printed. There are also file servers. So your disk might not be big enough. You can collect there. You can have a computer that keeps track of all the relevant files in an application. All right, how does communication goes? It is in layers. So there is the application layer. This is the layer where we are sitting as Python programmers. So we are sending a string through. We will do the hello world again, having two programs communicating with each other. Underneath the layers, at the very bottom layer, is the actual transmission of the bits and the bytes. In between, there is the layer responsible for chopping up any message in packets. And once that is done, the network layer actually takes care of figuring out where every packet needs to go. So there is there are the four layers that are here on the next slide shown. So when two computers communicate with each other, it could be direct, but it could be that there are intermediate nodes serving as intermediates between the computers connected to the network. So the application layer is where we are sitting. We don't need to be concerned with the division of the messages into packets, and we don't need to be worried about how the network is going to figure out how to route these packets through the network. Note that the notions that we have introduced last time for deadlock, and there's also live lock, packets may be circulating the the network. So it could be that some computers are too busy, caught up with sending packets, that they are unable to get their proper sending done. Okay, TCP, UDP. So there are protocols, two major protocols. We can ask for, and the protocol that we will be using will be the first protocol, the transmission control protocol. So that type of protocol works with acknowledgements. So the transmissions are confirmed. So there is actually there an additional protocol that is being surrounding the message sending. With UDP, there is just the sending of byte streams. UDP is very good for two computers in the same lab or same building that are connected almost directly to each other, where you are really connecting at the highest speed, so it's very much controlled. With TCP, it's very good if you are communicating computers over the internet, where the messages are broken up into packets, where packets may be sent through intermediate computers. So we distinguish also between connected-oriented protocols such as TCP and streamlined protocols, UDP. So UDP is connectionless, but it is streamlined. TCP is connection-oriented, not streamlined, but more reliable. Terminology. Sockets. Sockets are objects, programs used to connect computers with each other. They are originating from the Unix world, although sockets exist on all types of computers. So the nice thing about working with Python is also that we are at such a high layer that it doesn't really matter on which operating system we are working. There is the Internet Protocol. Every computer has an IP address. We touched on this when we talked about the Internet. There is the port number that both client and server must agree on to communicate. Some ports are reserved. Any ports lower than 1023 0 and 1023 are reserved for the operating system. An application program can pick any port between the ranges of that 16-bit integer. We will, in this course, work with localhost. You could be more ambitious and actually allow that your computer is, if you have multiple computers, that one computer is connecting to another computer. We will not do this in this course. We will just simulate how it can work on the local host. It may be that your firewall settings, so the first time I practiced this on my Windows computer, I had to click on something that Python programs could communicate with each other. Okay, to conclude, there is an analogy. So I started with the copper wire cables for telephone conversations. So if you have a telephone exchange, so you dial some company, and I think this is the UIC number for the IT help desk, or at least it used to be. So you dial, you get your call is answered by a receptionist. You ask for a particular person, here the computer center. The call is answered, and then the phone call is terminated. There is an analogy, so you connect first to some IP address. So the 127.0.0.1 is localhost. If the server accepts the connection, picks up the phone, the receptionist picked up the phone, then there is a connection. Then there is also the connection with the port. So that's the analogy for asking for a particular person. And then after that is established, then there could be a loop, an interaction between server and client. And then at the end, you close the sockets. So there's also a strong analogy with working with files. We connect to a server and then we open a socket and then we close the socket at the end of our program. So the same model is actually used in all types of client-server interaction. I have some screenshots. So I first did this on two terminals on a Mac. So what we will be doing is that I will be showing how to run a server program, and we will essentially do a hello world. The server waits a connection here, and then another program runs in another terminal will start up. So the server is waiting for a connection and will keep on hanging there until the client connects to that particular port. So here it is. The client is connected. So on top is the client terminal, and then at the other bottom now, we see what the connection has happened. So we received the request from localhost. So this is this 127.0.0.1 and the port number that was being used. Then the user has to type in something, and again the server waits for data to come. That's essentially the request. Handling the request, so there's just one message that is sent. The connection is established and whatever was typed up in the client window appears also in the server window. All right, very simple hello world, but two programs now. How is this working in Python? Python has the socket module. So Python is a framework language, comes with many classes. The class socket is one of them. So I'm importing socket as socket with a capital S. So you have to import the protocol that you will be using. Also on Unix computers, you actually are using AF underscore inet. So that's the commonly used address family. So you pick the address family, and then we are doing the confirmed the TCP protocol. So actually here it is the streaming that is done. That is the TCP. It's a little bit well, so there is the UDP protocol, there's the SOC diagram, and the SOC stream is actually the TCP. All right, so there are only very few commands that you need to know. At the server side, you will do the accept. You will do the binding there. So when there is the connection will be socket acts very much as a file object that we used to read and write to files. The close will be done by both server and client. The client will connect to the address where the server is. The server will listen for connections. So one can shut down. So the server can decide to accept or not. The server can, when it receives a request, it can actually check on the IP address of the sender. And can actually blacklist certain addresses. So there is then the sending and the receiving. There is a buffer that needs to be done. So working with buffers was shortly introduced when we did the file processing. It's also very relevant here. When we were working earlier, we encountered byte strings. So if you open up a file that you want to modify in a certain way, that you want to change, you actually are working with byte strings as well. So we will encounter this also here. All right, the last program I will show is a loop. We had the little secret guessing game earlier on. So the computer generates a secret number. That will be done by the dealer. So the dealer in this little game will allow a number of the player to make a number of guesses. Actually, it will be unlimited. The number is a single digit number, and the dealer will actually send feedback. So there is the divide and conquer that can be used. So this can be seen as a client server model. So the dealer first has to set up, so that acts as the server, and then the player acts as the client. So these things actually can happen simultaneously at the same time. So you will have two Python interpreters running on a multiprocessor computer, on a multi-core computer. These two programs run simultaneously. So this is not a computationally oriented course, but you could, and we actually will do that in the second part, you could actually realize a speed up for this. Here are some exercises. So instead of this, so there is the game of rock, paper, and scissors. That also could be played in a client-server manner. So there is a quiz, and these are old slides of Project 3. We had actually the computer literacy quiz, and you could also set this up as a client-server interaction. All right. You can simulate password authentication. So instead of just saying hello world, the user has to type in a password. The password could or should be actually encrypted at the client way. So actually the server only stores the encrypted passwords. So you don't send your passwords over to. So that's an exercise that also allows you a little bit looking into the encryption. It's outside the scope for this course, but in the later course we will get into this. Okay, so this is the first part. I have a Jupyter notebook prepared with the simple scripts. There is the hello world. I will still show the scripts. They are shown into markdown cells. I tried to run them in a Jupyter notebook, but it didn't really work. So I will switch to. So you cannot run this. I thought I could run this in two separate code cells back and forth, but something was not really working here. So just the point, but it is working within the terminal of the Jupyter Lab, so that is important. But let me explain the programs. So there is the tcp_server.py script. So this imports the socket class as socket with a capital S. We are going to use the general internet address family. We're using the TCP control protocol. So the host name will be blank. So this can run on any computer. We agree on a port number. So in some sense, this is our access code for any client. Any client program that connects to this application must use this port number. It might also be, if it doesn't work on your computer, is that the port number is not open. For a buffer size, 80 is still the default width of terminal windows, used to be. Okay, so then we have the server address. So there is the data that is defined here, and then we have the making of the socket. So the data is here defined, and then it is used. So you have the server address consisting of the host name and the port number, the addressing family and the TCP protocol, the binding of the socket. So we make an instance of socket, call it server, the binding to that address, and we can listen to two clients. So two programs can actually will be served by this. Um, can be served simultaneously. All right. So when this comes up, the message will be printed. The client the other program, TCP client, will connect. The server will accept it, and there will be another socket. A socket is another um, client is another socket, so we can actually use that client socket to communicate with the program that connected to this program that runs the script here. So what the server will do, it will wait for data. It will receive 80 characters at most from the client and convert a byte string into a string. And that will be placed into the final and then in the final message, and then the server will close. The code for the client is a little bit shorter. So here you see the client using the same port number, using localhost here. The client will connect to the server. So the server address is over here, localhost, not anything here, so it should be localhost. So there is the addressing family, same protocol, of course, have to be used. And the client will connect to the server. When the server accepts the connection and creates a socket at the server program, then the client will see the message and will be prompted to give a message to be sent. But first it must be encoded as a byte string. And then the client closes. Okay, I will run this in a terminal window of Jupyter Lab. I learned recently I will make another terminal. So I have two terminals now. But for the occasion, I learned how to split a terminal window in two sides. So this is convenient because I have two Python scripts and I have to flip back and forth, and I want to show also the interaction. So I'm now starting to type at the server part. Oops, Python. Let me do a clean start. So let me continue. TCP server. So the server is waiting for connection. Then at the other window, I launch the other script, TCP underscore client. And now you see that the connection happened. Perhaps I can scroll here a little bit. Oh no, I can't scroll. So what is the message? Hello, server. And you see the program ended. Perhaps it went rather fast, so let me redo it again and without first typing errors. So here perhaps properly, this had to be the server, the top window. So the server is hanging, waiting for connection. So now I'm go to the other window, clearing it. I will call the TCP client. And you see that the connection was accepted from localhost, and apparently in the program I'm not using the same port that I was using when I wrote the slides, but that doesn't matter. Hello again. So here is our hello world with two programs, a lot more code, but nevertheless, at the application layer, we don't need to get worried about all the technical details. With localhost, it works fine. Okay, I will demonstrate some more, and there is the dealer program, the little game. So let me clear both windows. So I have the dealer in our random number game. So the dealer almost fits on one window. And let me see if I can scroll a little bit. Or perhaps I shouldn't scroll. Then there is the player. So it doesn't fit into one. I now remember because there is a while loop here. What is shown here is that the beginning of the establishing of the connections. So there is the server on top, the host name, the port number. You see the port number agrees. For the client program, the player script here, the player actually needs to be using localhost, so it is going on the localhost. There is the connection from the dealer, so the player will make a socket to communicate with the server. So the socket is made here, passing the address family and the TCP protocol. And then the information of the server, its host name and the port number, is passed to the connect method. The connect method applied to the instance of the socket class. At the server side, so the server also sets up a socket. That socket is used to listen to communication, and that socket is used to accept connections. So here it is. So for the dealer has two sockets to work with. So there is the first socket that is used to listen and that is used to accept connections. As a result of the accept, the thing is, I mentioned that the server could reject a connection. So the server can, at this point, see the address of the player. So it can actually close the socket if that address is not right, but it continues. So the player socket, so the socket called player here, so the names are a little bit, so this is also, it's very important to point out the obvious. These are two entirely different programs that are running at the same time, or that will be running at the same time. The names that are being chosen, the fact that there is a player here and a player there, is completely arbitrary. So I could use any name for any sockets, so there is no communication here. Unless there is the messages that being sent. So here you see the game that will be played. The dealer here, the server, will generate a secret number. That's a random integer between a one-digit random integer, and it will actually print it out, so we can cheat. So what happens then at the player side? So here, what the player is doing is the user will type in a guess. It will send that number encoded as a byte string, and it will receive the answer back. So what does the dealer do? The server will wait for a guess and will receive a number that is decoded. So it is decoded first into a string, and then it is typecast into an integer because we want to compare. There is a reply being repaired by the dealer too low, too high, or found the secret. If the reply is found the secret, then the both programs will break. So in the last lecture, deadlock was mentioned, but you see also how deadlock can happen here when both client and server are waiting on each other. It's like in a conversation when nobody wants to say anything except when somebody in a reply to somebody else. So you have two parties at the table who don't want to speak first, and that is a deadlock situation. So here there are both two while true loops. Uh, the game will go on if the secret was never found. The game is also nicely interlaced. So when actually seeing the code or when writing the code, it's actually very good at keeping both windows open and seeing that for every receive, there is a matching send. So in the while true loop, the server receives a message from the player, first statement. In this while true loop, the player first sends a message. So for every matching send, there is a matching receive. For every matching send, there is a matching receive. When using message passing in parallel computing, that's a very important source for programming bugs when the programs are actually locked because there is no matching receive for a send or there is no send for a matching receive, etc. All right, let me run this. So at the top window, I will have the dealer program. So the game still has to start, so the dealer is ready. So let's play the game. Let's launch the other program. So now you see that the secret number is 4, so we can cheat or we can, so let me in a bisection mode, you know it's a single digit, so I enter 5. You see what the server, at the server side, the messages, the dealer actually received 5. Then the server is again waiting for an action from the client. It's too high, so 2. It's too low now. So the dealer received and sent the message. So the message is actually printed verbatim. So you could see this as a prompt. So the middle between 2 and 5, so let's say that this is 4, it found the secret. So this is a simple client-server interaction. Okay, and that's basically it. I can put up the programs again. So there is the dealer that is here, and then there is the client that I can put next to it. The client code, so the connection part is always very similar and it's relatively short. So there's a lot of stuff that happens, a lot of stuff that can go wrong as well. But if you're doing this on localhost, so if you have a computer with many cores, you could actually set up already in a computational oriented application, the server could act as somehow a manager of jobs and the clients can connect to it and ask for work from the server. So this is not too difficult to implement. and already achieving parallelism. So here you see the loops again. Actually, oh, okay, also very good that I show this. So this is the wrong program here. So there are the loops. Oops, I should have been here. So there is the player on top now. There are the matching loops for every, and there is also again the type byte strings. That's why we need uh, the encode when we send something, and when we receive something, we have to do the decode. Otherwise, it won't work. All right, I'm 40 minutes in. I'm actually done. What is important of this lecture is the terminology. Every slide that I actually showed is kind of a very summary of an entire, so I could spend a lot more time in this, and subsequent courses will do this. But the second important thing is also that with Python, that you can experience this with very little code. You can write programs that communicate with each other, and so understand another way of building truly parallel programs while with two Python interpreters connecting with each other.